Okay, so yeah, it's my pleasure. Welcome everyone. It's my pleasure to welcome Sean Welleck, who's a postdoctoral scholar at the University of Washington and also the Allen Institute for AI. And he's done a lot of great work on generating and reasoning with language, and I think you'll be talking about some of that today. So yeah,
That
it's
was an
great
hour
to
ago.
have you. Sorry?
Wait, no, 3 p.m. Eastern time wasn't, yeah, 2 p.m. our time.
Oh, I think, sorry, what is there someone who's, yeah, sorry about that. But yeah, it's great to have you here and whenever you're ready.
Okay, great. Yeah, thank you for the introduction and for the opportunity to give this talk. So yeah, today I'm going to talk about some exciting work we have on bridging informal and formal mathematical reasoning using these really large-scale neural language models. So just to start off, like in machine learning, we've seen a lot of exciting progress and impact in everything from science to engineering, where we have these large models helping us write code more quickly, and even to education, where AI is starting to have an impact in making education more accessible and things easier to learn. And today I'm going to talk about mathematics, which is an interesting area because it intersects with all three of these. As we kind of all know, math is a key tool in the scientific process. It's useful for solving problems in engineering. And it's also at the center of a lot of our education. And so AI is starting to have an impact in math as well, ranging from discovering new algorithms to even helping people write and communicate proofs, and also to help with learning something which is kind of infamously difficult to learn. But I think that there's also an exciting aspect, which is that trying to build machine learning systems that are capable of doing sophisticated forms of mathematical reasoning actually requires us to solve some core problems in AI. So for example, whether it's like solving a simple math word problem or trying to teach someone math or write a sophisticated proof, these all kind of draw on sophisticated language understanding, problem-solving abilities, as well as aspects of kind of symbolic reasoning. And all three of these are very much still, of interest and present, even with these really large-scale models that I'll be talking about today. And so this talk is going to focus on one aspect of math, which is really central, and that is mathematical proofs. So I want to start with a simple example and kind of reflect on like, how do we actually know that 1 + 1 = 2? And so what we can do is we could supply a proof that convinces ourselves or convinces someone else that this is true. And so the proof could look something like this. We could say, it's pretty obvious that if you pick up an apple and you pick up another one, then you've kind of picked up 2 apples. On the other hand, we could kind of write down in extreme detail in a logical formalism a proof that 1 + 1 = 2, which was done here in this Principia. And the kind of larger point that this is highlighting is that when we think about writing these proofs, they kind of open up this spectrum between the informal language, which is intuitive but often ambiguous, and something that's formally specified in logic, which is precise and explicit. And so it turns out that like when we think about building a machine learning system that could write the type of proof here, which could be useful, say, for a student who's struggling while working on a proof like this in a textbook, or like a proof that we see in something like the International Math Olympiad, like the one shown here. This kind of tension between the informal and formal is going to come up. And by that, I mean that like we could think about building a system that can prove these things purely in the informal, ambiguous language space. And in that sense, we can just treat these mathematical problems as just sequences of text and try to generate them with these really large language models. So what is a large language model? Just to make sure everyone is on the same page. So at a high level, these are really large neural networks that are trained on kind of vast corpora of text. So this might be like a large proportion of the internet, or it could be all the code on GitHub, etc. And the key idea behind how they're trained is to essentially take each prefix in the text and then just have them learn to predict the next token. And although this is kind of conceptually simple, one way of thinking about what this is doing is it's actually training the model on a massive implicit mixture of tasks. Like here, we could say that this task that the model has to learn has to do something with, learning how to engage in a dialogue. And similarly, if we look at, say, a page from Wikipedia, then here, if the model is given this prefix 1 + 1 equals, then arguably, like forcing it to learn to predict 2 causes it to learn something, whether it's memorization or something more general about this mathematical fact. And so you can kind of imagine that if we have millions and billions of these tasks mixed throughout the training data, then it's possible that these language models learn something interesting. And so what we get at the end is a flexible generation system where we could essentially give it some arbitrary text and have it generate some one or more completions. And so this kind of generic interface is starting to be used for a variety of tasks. And so in the area of math, most of the work in, these are flexible. And in the area of math, most of the work, at least in the natural language processing area, has been focused on these kind of grade school level math word problems. So these might involve like reading a few sentences that specify some problem, and then doing some arithmetic that kind of parses the problem that's inherent in the text and comes up with some solution. And so as we scale these models up larger and larger, and with some additional, like generation tricks that people have discovered, we're actually starting to see pretty reasonable performance on these types of tasks. But if we actually look at some of the mistakes that these models make, it could lead to something more worrying if we're using them for more sophisticated tasks. So here, for example, we're basically showing the intermediate steps of reasoning generated by one of these really large language models. And so you can see that at the surface level, it generates this equation, which is really convincing. 3 × 25 × 8 = 300. But then if you actually like run that through a calculator, it's off by 1 digit. So the answer turns out to be 600, which kind of makes it completely incorrect. And so even with these extremely large models, it still turns out to be useful to kind of have them call out to some external calculator to do a simple computation like this. And so the question is, like, in more sophisticated settings, like say a mathematical proof, we might have kind of more generic uses of these multi-step equations. And so it's not clear whether this kind of informal approach of just training on massive amounts of data will give us what's required to do this type of generation or reasoning. Another example, we can look at an output from a dialogue model. And again, both these are taken from actual papers. So here the model says, my favorite Elvis song is Love Me Do. And it turns out that this was actually released in a completely different date by the Beatles. And so basically what the model did is kind of hallucinate some fact, which again, at the surface level looks, pretty nice. And so again, even with these extremely large models, it's still useful usually to have some form of retrieval, either like a separate retrieval model or even like a call to a search API. And it turns out that like in these proofs, there's kind of an analogous situation where a proof might refer to some previous theorem or some previous mathematical fact. And so the question is like, will the model have enough kind of grounding to be able to memorize all these and use them correctly without hallucinating things that are just false? So I use this word grounding, and this is kind of just a useful phrase to summarize cases like this, where the model kind of learns to imitate a lot of text, but it doesn't have the kind of deeper form of grounding that like a calculator would have for a simple computation, or that we could get by like a retrieval system, which actually looks at a document related to a fact. So the first part of the talk is going to look into this question of trying to prove theorems just informally and try to add additional forms of grounding through background documents. Then in the second part of the talk, I'll talk about some really recent work that we've done on trying to get really strong forms of grounding by actually taking informal proofs and translating them into formal verifiable proofs. So on the informal side, the first thing that we did was take the largest language model that was available to us. So if you've heard of these GPT-3 models, and fine-tune them on a data set of theorem and proof pairs. So a couple of years ago, we had assembled a data set, which basically takes about 20,000 theorems and proofs from the site called ProofWiki. And you can kind of tell by the blue text that this is similar to Wikipedia, except for math proofs. And it kind of links to other pages within the system. So then if you use this model after doing this fine-tuning procedure to try to prove some new unseen theorems, and we kind of ensured that the unseen ones were split in an intelligent way, along with its kind of like standard approach to generation, which is just selecting the most probable next token. Then it starts to generate something which looks kind of reasonable. So it says, we're going to start a proof by contradiction and suppose x plus 5 is even. Then it uses the definition of even integer. But then on the third line, it actually invents this fact that an odd integer plus an odd integer is odd. And so if you think about like 3 plus 3, that equals 6, which is even. So this is just completely false. And so it's kind of an analogy to the case we saw before, where the model kind of invented some fact about Elvis. So then, like, as a result, the resulting proof to a human is going to be invalid. So to overcome this a bit, we look into adding additional grounding in the form of references from ProofWiki, and then use a more sophisticated search procedure for ensuring that these references are included in the proof. So what do I mean by that? So here we now additionally give the model at training time and at generation time a set of references, so definitions or theorems that are relevant for the proof that it's writing. And so here in this example, we have like the definition of odd integer and proof by contradiction. And in more sophisticated proofs, this might involve like previous theorems or more arcane definitions. And so these can either come from a retrieval model that we've trained to retrieve things that are relevant to a proof, or they could come from a human. So we could use a human written proof to get these useful references, or use the system sort of interactively. Then we do a kind of less naive search procedure to generate the proof. And I won't go into much detail here, but the idea is we basically generate multiple steps, multiple next step candidates, and then we choose next steps based on how many references they contain. So in other words, like we do this kind of beam search procedure and score the different candidates based on their reference coverage. And so with these two components in place, we can look at this example again. And it kind of starts off the proof in a similar way. But now instead of hallucinating the fact at this step, it kind of concludes that the previous step results in a contradiction and then concludes the proof. So now, like, we want to quantify these differences more systematically. So we used automatic metrics, like during model development, but then we actually did a human study with 15 mathematics students from University of Washington. So these were undergrads, master's students, and PhD students. And we kind of held a training session and built an entire interface for annotating each step of these proofs and a rating of whether they were correct or useful. And so here we could see that, for instance, the GPT-3 model in blue ends up being like much less correct and useful than these like knowledge grounded models. And so here usefulness means that the proof might be slightly incorrect, but the annotators asked to say, like, if they were proving the theorem on their own, would this still serve as a kind of useful hint for proving it? And so you can see here that kind of adding in the search as well as the knowledge grounding leads to more correct and useful proofs. And so this was kind of surprising going in because this problem kind of hadn't been studied and we really weren't sure whether anything from these models was going to be correct and useful. On the other hand, you can see that like they're far from perfect, and this was on a kind of held out a smaller subset of the proof wiki that we held up for evaluation. So I'll talk about the limitations in a second, but like this type of system could be potentially useful in some interactive setting. So we started to look into this, and we're actually still looking into this further, where we use our system to kind of propose multiple next steps in a proof. And then we can have a human interactively choose which ones that they prefer. And so in this sense, like the model is still able to make mistakes, but as long as something reasonable is within its top few predictions, then this could potentially be helpful as like an interactive tool for working on these types of theorems. So the other thing that our study kind of revealed is that although these models are capable of proving some theorems, there is still an issue of like trusting their outputs. So in two different senses. So the two methods that we introduced do reduce the reasoning errors. So here's like reference-related errors, equation-related errors, and other things like skipping steps, etc. However, you can see that like the error rate is still above 0. And in these proofs, it's often kind of tricky to tell whether something is incorrect or correct. And so one option is, again, to use this as some interactive system. But we could ask the question of like, what if we want these systems to prove like long and complicated theorems? Then this issue of trustworthiness kind of comes up. So here's an example where, for instance, the difference between this incorrect proof and the correct one is very subtle. So it turns out that like this rule only allows you to conclude that -0 is greater than -1. And so saying -1 is less than 0 is actually incorrect in this context. And so like the larger idea is that, you know, within these sophisticated proofs, the model might still make slight mistakes that could become hard to detect. And so another question is like, you know, does this go away if we just make the model really, really large? And so for that, there's kind of a useful case study recently. So Google developed this model called Minerva, which is massive. So it's over 500 billion parameters. And they essentially train it on massive amounts of math-related text from the internet, as well as archive. And this model, again, showed some very impressive capabilities. But we can still look at some of its predictions and see these types of the same fundamental type of error popping up. So here, for instance, the model gives you a correct answer to this question. But then if you actually look at its intermediate reasoning, it contains an error. So here, for instance, like this computation is incorrect. But as they get more sophisticated, it's often difficult to even tell like which part is incorrect without really deeply thinking about the output. And what they showed is that actually these kind of false positives increase with the difficulty of the problem. And so in other words, like if we as we start using these for more sophisticated things, then this issue of trustworthiness actually becomes more and more you know, of an issue.
Sorry, there was a question about, I think a few slides ago, the user study that you talked about. Someone asked if it includes proofs that appear in the training sets or if it's like test set.
Oh, okay, yeah. So what we did is we look at the reference structure in ProofWiki, and we basically have test theorems that are leaf nodes. So they don't appear in the training set, and they've never even been referenced by other theorems in the training set. So they're kind of completely unseen.
Okay, thanks.
And so this kind of motivates getting some stronger form of grounding. And so for that, I'm going to talk about our next project, which tries to go from this informal space where we can do this flexible form of generation to a formal proof system, which has a strong form of logical grounding and verifiability. So what does this formal system look like? So just to make sure like everyone is on the same page with these, let me just give a brief high-level introduction to these. So in the kind of modern day, we don't do what was done in 1910 and write down things in 100 pages of logic. We can use these formal proof assistants or interactive theorem provers. So like if you've heard of like the Lean prover or Isabelle, these are some, or Coq, these are some popular proof assistants. And basically the math is written in a program-like language. And then at a high level, you could think of writing a proof as being similar to some game where we basically take different moves and it translates and it transforms the current goal. So here, for instance, the move that we took was to flip the right-hand side of the equation. And then we can take another move, which kind of subtracts both sides. And that gives us something which is trivial for the system. And so the idea is like this entire chain is grounded in some underlying logical formalism. And so we're able to verify whether this proof is correct. And then we can ask the question of like, how can we automatically prove things similar to what we were trying to do in natural language? So there's been a kind of rich literature on automating these formal proofs. And an example that we'll use here is called Sledgehammer. This is in the Isabelle proof assistant. And you could think of what this is doing as basically taking the current theorem that you have, compiling it down, and then calling a bunch of external provers. So one's based on first order or higher order logic, SMT solvers, and things like that. And this can actually be really useful as you're using one of these systems to write a proof yourself. However, if we look at kind of some real theorems, then we might want to get to something like which is shown on the right-hand side. And it's kind of dimmed out because we shouldn't try reading the whole thing right now. But the idea is like the search space to arrive at this proof is incredibly large. And so these types of methods like Sledgehammer would be insufficient for fully proving this theorem from scratch. And so instead, some recent work has actually used language models to try to suggest next steps in these proofs. And so here, this kind of cuts down the search space by having the model suggest next steps. But we again run into a kind of issue with these methods. So unlike in the informal space where we can draw on, say, like all of arXiv or all math web pages, these formal libraries of mathematics are relatively small. And so far, most of the, or essentially like all of the work in this area in using these language models have used really small models within a kind of sophisticated tree search procedure. And in particular, they haven't drawn on these really large language models, which kind of generate things in one shot. Was there another question in the chat? Let me see. Oh, just saying thanks. Sounds good. So what we're going to look into is trying to get the kind of best of both worlds and integrate these larger language models for writing these formal proofs. Okay, so I'm just going to put one more example up here, and I know it's kind of the most theorems you've maybe had to prove during a talk, but so this one just has to do with greatest common divisors and least common multiples. And you basically want to prove that the number is equal to 70. So in our pipeline, we have a multiple stage procedure. And so the first step is going to be to generate some informal proof using, like in our experiments, we use this really large Minerva model. But instead of considering it as being the final output, we're just going to consider it as being a draft. Then we use the draft to create a high-level proof sketch. And so what is a proof sketch? So a proof sketch is kind of guided by contents in the informal proof. So here, for instance, this equation 10 times 280 is basically taken from the informal proof. But you could see that the lower level proof of this kind of smaller conjecture here is left unspecified. And so if you do this for the entire proof draft, now we kind of have the skeleton of the high level steps with the lower level details of how to prove those steps left to be proven.
Wait, how did you extract these intermediate steps from the informal draft? Is that an automatic thing that?
Yeah, so I'll explain that in a
Okay.
second. So yeah, it's supposed to raise a sense of mystery and how it's done. But then like, suppose we have this, then the idea is like, what this does is it essentially cuts down the search space into these smaller steps that become tractable for even these off-the-shelf methods like Sledgehammer. And then at the end, we have something which is fully verifiable.
Mhm. Yeah, sorry. So in Sledgehammer, you're just trying to show that the previous statement proves the next statement. Is that true?
Yeah. So basically here, if you look at C2, then it's just trying to prove the statement in C2, given everything previous.
No, everything previous. It's not local. Proofs are
Yeah.
generally local. Right? So I'm just wondering if you're using the fact.
Yeah, so this is able to refer to, for instance, C1 improving C2.
Thank you.
Then another thing that I forgot to put on the slide is we also assume that the formal statement is given. So I'll have an example later. So we have like the informal statement of the theorem and the formal statement, and we're trying to come up with the formal proof. So then, yeah, these are the kind of three components. And there's this question of where do we get these, how do we do this mapping between drafts and sketches? And in particular, like this paired data of drafting and sketching just doesn't exist. So typically, like in translation, if we want to translate between English and French, we'd assemble a paired data set and train a model, but this doesn't exist in our case. So we're going to build upon a kind of simple but surprising finding in the past couple of years, which is that we can use these large language models to actually quickly learn to do these tasks. So in particular, we use this model called Codex, which is trained on a large amount of code. So something like all of GitHub. And what's been found for these types of large language models is that certain tasks they're able to learn just in context. And so what does that mean? It means that we provide just a few input-output examples, then provide them with some test input, and then have them produce some test output. And so what we found here is that surprisingly, like this Codex model is actually able to learn to do the sketching through just a few examples that we provide in its context. So again, if you want, I'm gonna show the details here. If not, then feel free to tune in like 30 seconds. But here's like what we actually would give the model. Oh, yeah, here it is. So you could see here that we give it the informal statement, then an informal proof. And then here's an example proof sketch that we give. So you could see that like we have the statement of the problem, and then the sketch, which has comments that kind of align the informal proof with what is shown in the formal proof. Then these little red indicators just mean that that's what's left for the automated system to fill in. And so what we essentially do is write 20 of these examples. So we wrote like 10 number theory ones and 10 algebra. And it also turned out to be important to have these comments, which show the alignment. And then we essentially just take 3 of them at random and provide the model with some new statement and informal proof and have it generate a sketch. And
And just to make sure, this is like the GPT style, like you're not fine tuning the model. This is just providing it in the prompt.
exactly, yeah, just
I
in the
see.
prompt.
Yes.
Yeah. So yeah, certainly in the future, it's going to be interesting to try to train a model to do this. And typically, like if you have a task and you're able to assemble enough data, then we're still able to beat the few-shot models. But at least here, we're able to just draw on this few-shot learning capability. So these are the three components. So we have the Minerva model, or you can use a human written proof. We have this sketching model, which is Codex. And then we have the automated prover, and we use Sledgehammer. And what's nice is we can actually draw on the fact that everything at the end is verified and generate like many candidates. So specifically, like we can generate many potential proofs, many sketches, and then just try to verify them all and see if anyone checks out. And so that's our approach. And then just as a kind of summary, this does draw on these really large language models that are operating in this informal space. And then at the end, we get a formal proof, which is, in some sense, grounded. So to evaluate this, we used the standard benchmark in this formal theorem proving, mathematical formal theorem proving area. And it consists of about 500 problems from math competitions, so AMC or International Math Olympiad, as well as some from undergraduate level courses. Then we use this proof assistant called Isabel. And so Isabel has this sledgehammer functionality that I mentioned before. And the style is, if you've been looking at the examples, this kind of declarative style where you can have these intermediate conjectures that such that it's kind of possible to have this alignment between the informal and formal. And then as our baselines, we're just going to try to prove these theorems directly with Sledgehammer, as well as some common heuristics, and also compare it against the current state of the art for the mathematical theorem proving in Isabel. And how you can think about the state of the art method is it's essentially trained on the available Isabel data, so the archive of formal proofs. And then it's additionally trained with a reinforcement learning-like procedure. So specifically, it's called expert iteration on additional data. And so this is a kind of strong baseline for operating purely in the formal space.
So there was I think, two questions. First of all, someone asked how you handle errors in the sketches generated by Codex. So if there's syntax or semantic errors, do you do anything about those, or?
Yeah, so so I guess two things. So first is the sketch still has to be closed by the formal prover. So if the formal prover fails to, parse the theorem, then it would just be discarded from the search. Does that make sense?
As in you'll just give up, or for that problem, or will you try a different strategy to solve it?
Yeah, so in our system, we'll generate 100 different candidates. So 100 different sketch candidates.
Okay, got it.
And then if one of them, say, has a syntactic error, then it'll just get filtered out because it won't be able to be closed in the end.
Got it. And then, yeah, there was one more question. Did you use any special sampling techniques to improve the diversity or coverage of the candidates?
Yeah, that's a good question. So we experimented with a few things. So but all of them fairly simple. So with these models, you can adjust the sampling temperature, which means that like if you go to a lower temperature, then it'll be more focused on things that are more probable, but you'll have less diversity. And on the other hand, you can increase the temperature and get more diversity, but then they might be kind of lower probability. So we tried a few different temperatures, and then we also tried just randomizing the set of 3 prompt instances. And so in the end, what we actually do is select 3 instances randomly, and then use a fairly low temperature. And so a lot of the randomness comes from just the selection of prompts, actually. And we found that this versus adjusting the temperature end up performing roughly similarly.
Great, thanks.
But yeah, there's definitely more to be explored there. So then, yeah, you can see that here, if you use the sledgehammer procedure, like we were saying before, it is able to prove some of them, but it's far below what the kind of neural prover can do. Then if you use our pipeline, here's using model generated informal proofs, then it's able to exceed the state-of-the-art here in Isabel. So one question is like, what if we use codecs to just generate the proof directly instead of generating a sketch and then calling the automated prover? So this turns out to do much worse than doing the intermediate sketch. And I'll show an example later. Maybe I should put it now. I'll show an example later that gives you an intuition for why this is the case. Essentially, like some of these lower level proofs probably don't appear almost anywhere in Codex's training set. Another thing that we found is that getting these drafts from the neural system can actually solve the same amount or even more problems than using a human written draft. So what we do here is in the orange line, we essentially use Minerva to generate many informal proofs and then just translate them into one sketch. Whereas with a human proof, we translate it into many sketches and kind of keep the budget the same. And so you can see, as you increase the number of attempts on the x-axis, the 2 lines eventually meet. And if you generate like over 130 different possible informal proofs, we eventually slightly outperform using a human proof. And kind of both settings are interesting because a lot of the time, there's several projects aimed at formalizing mathematics. And so sometimes in practice, you'll have a human written informal proof. And so this blue line is showing that our system could be useful for those settings. This one is again just how to allocate the sketching budget. Maybe I'll just skip over this one quickly, but we essentially found that generating more drafts ends up being slightly better. But if everyone is still with me, I wanted to step through a kind of sophisticated example just to give you an idea of something that the system can do. So here, for instance, is a problem from the first International Math Olympiad. And so the problem is to prove that this fraction here is irreducible for every natural number. And so first we can look at the informal proof, which was generated by the Minerva model. And if you were to kind of step through the proof, then it turns out to be, a valid proof. But let's look at how it actually gets translated into a sketch and eventually into a formal proof. So again, the system is given the formal statement. And again, this comes from the benchmark, and the benchmark gives us the statement of showing that the greatest common denominator of these two numbers, of these two things, is equal to 1. And you could see here at the first step, the sketch model kind of indicates this alignment between the formal proof and then something that appears in the informal one. Then for this step, the formal part is fairly simple. The sledgehammer just calls this kind of built-in heuristic called auto, and it's able to move to the next step. Then if we roll out the entire thing, you can see this interleaving of the blue, which is the sketching, and the purple, which is the formal proving. So for instance, here again, we see this alignment. And here we can see a kind of sophisticated, more sophisticated lower level proof found by Sledgehammer. And so this can give some intuition why, using the large neural model to directly prove the theorem, some intuition for why that might be much worse than our kind of pipelined approach. This kind of complicated composition of these low-level facts probably doesn't occur much or at all on the internet, and so it's difficult to kind of fully learn this behavior to the same level that the symbolic procedure knows how to do it. Okay, so in summary, if we kind of zoom out, what we found is that these really large language models are to some extent capable of proving some sophisticated mathematical theorems. And as we discussed throughout the talk, the kind of key words here are capable and some, and there's always going to be a trade-off between the flexibility of the system and then how much we can trust its outputs. And of course, this trade-off comes up in many different places as we think about using these generative models. For instance, in code generation, we could imagine having provably correct code versus like sampling from a generative model and putting it into our production system. And so, thinking about these trade-offs really is becoming more and more relevant as these generative models become more powerful. Then we showed that this idea of sketching helps to bridge the gap between this informal space and the formal grounded space. And there, if we kind of zoom out and think about how to interpret what the language model is doing, then it's kind of serving as providing this kind of high-level sketch of what the formal proof should do and leaving some of the details left to the automated provers. So I just wanted to briefly comment on just like 3 different areas for the future. So one is just staying specific to this math setting. One area is to branch out in the generality. So with these competition problems, they're still fairly in a limited domain. They're kind of designed not to, for instance, like refer to some theorem from topology. Whereas something like ProofWiki or a math textbook could draw on and test additional background knowledge, which would introduce new challenges for these models. And then similarly, being able to formalize things from a textbook, for instance, again, makes these systems more useful for people interested in formalizing mathematics. Another area, another way of looking at this is that, we have to think about how we improve these systems further after we've, for instance, trained on all the text on the internet. And so there we could look to additional forms of feedback And so here we could think about the formal system potentially providing some feedback signal that could be used to update either the formal model, the translator, or the informal model. Or our kind of initial exploration with the human collaboration could also lead to additional forms of feedback from a human. And then third, just a higher level comment, which is like one thing that we showed is that actually decomposing the system into 3 different parts led to an overall system that was more capable. And so these larger and larger language models are very, very exciting. But at the same time, like it's also exciting to think about these models as being one part of some larger system. And so there, the balance that we have to figure out is like which part should be neural, which parts should be symbolic, and how to get these systems to interact with each other. And so both of these projects were big team efforts. And so a big thank you to all my collaborators. And it was a lot of fun working on these. And you could see the links to the 2 papers at the bottom. And I'm happy to take any questions.
Yeah, thanks so much for the great talk. So I think there were 2 questions that we didn't get to in the chat. So the first one was asking, how do you handle generalization for proof techniques? So for example, assuming that you've seen induction on 2 variables, whether there's a way, how do you generalize to induction on 4 variables?
I see, yeah. So I would say that so far, the thing that we've looked into is just the variation that comes from the examples in the prompt, sorry. So for example, if we were to have no induction proofs in the prompt, then this would probably lower the chance that the model would produce induction proofs. So we do have some amount of diversity in the prompts in the sense that like we cover number theory and algebra, which are covered in this benchmark. And we have a few examples of induction. But beyond that, we just rely on the diversity from sampling from the model. And so, yeah, again, there's definitely more to be explored.
Got it, thanks. So the next question, I'm not sure. So it's asking, Sledgehammer may prove more complex statements than what's acceptable in the line of proof. How do you handle that? The proof is correct, but not really a proof. I'm not sure if I got that right, Pramadhu, if you want to clarify. But yeah.
Let me see. Most acceptable. Yeah, if you want to clarify, that would be helpful. I think there's a few ways to, there's a few things to say. So like one is, it is possible that the proof, that the formal proof ends up, for instance, like not using the informal proof. And so for that, we did some analysis. I would say that kind of informally, it tends to happen on simpler proofs. So for instance, if it's like a straightforward induction proof, then the model might be able to just generate something and none of the inline comments from the informal proof are used. Whereas in the more sophisticated ones, they tend to be used. Does that kind of help answer?
No, so I was more worried that it may not be one line of proof, really. I mean, it may be something which, you know, Sledgehammer may reduce it, which actually requires, let's say, 1,000 lines of formal proof. In what sense have you proved it if you just used an automated theorem prover to prove it, right? So maybe that's not your goal. Is the goal to create something which looks like a proof or not?
Yeah, that's a good question. So the kind of story was from a informal proving perspective. yeah, ultimately, it's kind of getting a formal proof at the end. And so, like you're saying, there's no restriction that it necessarily has to reflect the informal proof. Yeah.
Not the informal proof, but what is a step of a proof? Usually, every step of a proof has to be intelligible to the reader, right? Or maybe you don't require that. Maybe you just require that it be correct.
Yeah, exactly. So here, ultimately, we just require that it's correct. So yeah, you could imagine having a really powerful automated prover that just proves a really large gap.
Yeah.
And then like if a human read it, the gap would still be.
So do you have any evidence that, let's say, the example that you presented was not directly provable by the automatic theorem prover?
Yeah. So in the one bar chart, we use the automated prover along with additional heuristics, and it gets about 20% performance on the benchmark, whereas our system got near 40%.
Okay, thank you.
So the next, I think someone had a couple of questions, but in the interest of time, I might just summarize. So are there, can you say a little bit about what happens with complex theorems and where the proofs might need to be quite big? Can you handle these kinds of problems, or have any idea how to scale to that?
Yeah, so yeah, it's always difficult to quantify. So I'd say qualitatively, there are examples where the proofs are very long, and you could think about like the reason for that is as long as each gap is still relatively small, then our system is kind of decomposing the problem into smaller gaps.
But you still have this codex step at the beginning that has to generate the large sketch, right? So if the sketch becomes long, then is that still like maybe how large of a sketch can you handle?
Yeah. So yeah, it's hard to say quantitatively. Yeah, I would say like as long as you could imagine like some example where it's like a long derivation, and so each step of the derivation is kind of tractable for the formal prover, and there it almost doesn't matter how long the sketch is. Yeah.
I had like another question, like what was the reason for choosing Isabella over like some other proof assistant like Coq or something else?
Yeah, so Coq would also work well with this, at least in theory. So yeah, Isabel, we liked it because it had this kind of declarative style, as well as the sledgehammer functionality built in. And so again, like in theory, we could use any formal prover, but for kind of doing the initial version of this project, Isabel was kind of a perfect match.
So yeah, I don't know if you need to go, or there are a couple more questions if you have time, but we can.
Yeah, sure. Yeah.
Okay, so yeah, Clement asked if you've done any studies on similarity of problems and basically similarity of the training and test set of problems and proofs, whether there's overlap. I think you touched on this earlier. But.
Yeah, so in the informal proofs case, yeah, I mentioned how we split it according to make sure that the theorems were not referred to anywhere in the training set. Then in the formal proofs case, we use this benchmark. And so the benchmark consists of different competition problems. And so there's going to be, a similar domain for the competition problems, but there's not going to be overlap in the exact content of the problems themselves. Then in terms of the overlap between training and testing for the for the large language models. So there we kind of had to defer to each component of the system. So the Minerva model, they did their own analysis in the paper, actually with these competition level problems. And I don't think I'd be able to like do it justice here, but I would say like you can take a look at the Minerva paper there. And then the Codex model was actually trained before the formal benchmark was released. So we do have some confidence that it's actually generating novel things here.
My
Great,
question
thanks.
was more
Oh,
on the.
yeah, sorry, go ahead.
Yeah, can I ask a follow-up?
Sure.
Well, my question was more on the line of like, to what extent, like what part of the questions, like in a sense, they added distance. Like, for example, it might be a different problem, but only the constants might be changed, or only the wording of the problem might be changed. As in, like, to what that was just the aspect I was.
Yeah. So we didn't. So on the data set, since we were using the existing benchmark, we didn't do any additional analysis of that type. But I would say that like on this benchmark, it's drawn from different competition problems. And then it's still a relatively small benchmark. It's less than 500 problems. And so at this point, like people have looked through them. And yeah, I guess all I can say is that there's not too much overlap in the exact problems to the point where they'd be like the same, but with different numbers.
Thanks.
So yeah, there are two more I see. So the next one, generating induction hypothesis can be pretty difficult for theorem provers. Do you have inductive proofs where you had to come up with some kind of induction hypothesis? And what did your technique successfully solve these?
Yeah, so we did have a few induction examples. I think, so I didn't have them in the talk, but we do have two examples in the paper, in the appendix, if you're interested. So yeah, it does show some ability to do induction. But yeah, we haven't kind of systematically characterized the ability to do induction.
And the last question, the pipeline seems highly dependent on Minerva providing a reasonable proof overview. So did you, are you able to decouple this or be robust to bad summaries? And what happens if Minerva is less powerful? Does this still work? And when the model fails to create a proof, how often is it because of a bad summary? Do you have a sense?
Yeah, so, okay, so yeah, there's a few things. So yeah, first is like we also study the setting where we have a human written proof. And so there the system is able to perform well with the human written proof. Then in terms of Minerva, we studied the various sizes of Minerva as well as using Codex to generate the informal proof. And so we found slight decreases in the performance from moving to say like from the 62 billion parameter model to 8 billion parameters. And then Codex was similar to 8 billion Minerva. So yeah, like we are using these powerful large language models. And we did see a slight degradation going from 62 billion to 8. But like the models are still able to do something reasonable at 8 billion. But yeah, certainly the underlying informal prover, if it's guiding these sketches, then it has to be reasonably sophisticated. So hopefully that answers that part. And then as far as when it is a bad summary, so let me see, I might have actually, so we did some analysis on this in the paper, and maybe I won't be able to go into it in detail here, but we basically looked at 50 different drafts that led to a correct proof, and then did some human evaluation on them. And so 29 of them were fully correct. And then 21 of them, I would classify them as other. So they might have had like one line that was incorrect, and it actually got corrected by the auto formalizer, meaning that like the line in the proof was slightly off, but then the resulting thing in the formal proof from a human perspective was reasonable. And then the 13 other cases, the proof kind of got ignored by the auto formalizer. So these, again, some of them were simple cases where, yeah, the auto formalizer was able to just use, say, like a standard induction argument and didn't have to look at the informal proof.
Okay, yeah, I think that's all the questions. So thanks so much again for the great talk, and thanks everyone for joining, and I'll see you all next time.
Okay, thanks.
Thank you.
Very impressive.